starting here, you click on each of the systems. I'm going to like insert a new schematic for you. So the pan here, when you click on pan, it gives you the ability to be able to drag the schematic or your design anywhere around the screen. And then when you click on rotate, it gives you the opportunity to rotate the schematic. And then orient gives you the various orientations you can choose from. We have top, bottom, right, left, front. Yeah, when we do the design to a point, you appreciate this one's better. So we are going for 2.5 gigahertz. Let's do one. 3 gigahertz. So
yeah, do 1 gigahertz.
3 times 10 to the power divided by 3 times 3 times 10 to the power 9. This is 0.1. And this is lambda, so lambda divided by 4 is 0.025. So this times 10 to the power. So that's 25 millimeters. That's going to be a monopole height for 3 gigahertz. When you first come here, these are the various shapes you can use. So this is cylinder. So you click on cylinder, you come to the midpoint, you click, you drag, and then drag to the top as well. So after that, you come here, and then you can change the name of the cylinder to monopole. And then the material, you click, it will be having vacuum, so you click and then you type PEC. And then you select PEC. And you can give it any color you want to like. And then you increase the transparency. It doesn't do anything to it anyways, but when you increase it, it makes it possible for you to see through the shapes. So you come to create cylinder, and then you change the dimensions. So our monopole height, sorry, this is the height. The height is 25, and then the radius. Now we are going to choose. So you see that the cylinder is lying exactly at the origin. So that is why you have 0, 0, 0. Now we want to elevate the cylinder. You see that the red is the x-axis, y is the green, and z is blue. So if you want to elevate, it means you are going to change the z parameter, or let me say the z value. This is x, y, and z. So if this z, then means you are going to change the third value there, and then we are going to elevate it by 0.125. 0.125. And whatever you choose for your elevation, half of that is going to be your radius. So if we have 0.125 divided by 2 is going to be our radius. 0.0625. So after that, you see that it has elevated the cylinder. If you can't see it or after we just click fit to fill, and then it makes it smaller for you. just select rectangle. Okay. You come and then you change the name to brown. And I want to give you and we change the dimension. So we are supposed to position this such that the cylinder will be lying exactly at the center. So I want to use the dimension. So what was our lambda? 0.1 divided by the lambda was 0.1, right? No. Lambda was 0.1. So we used 3 guys. So 3 times 10 to the power 8 divided by 3 times 10 to the power 9. Yeah, 0.1. So lambda divided by 2, 0.5. So this is going to be like the value around the dimension of your ground plane. So you come here, this is 50, but I want to use 40. So I'll go 40 by 40. And then the position. Now, if the dimension is 40 by 40, it means that the whole length of this is going to be 40, and then the whole length of this is going to be 40. But we want this to be positioned such that the cylinder will be exactly at the middle. If that's the case, then it means the X, Y, and Z values here will have to change. So the first one is going to be negative 40 divided by 2. Negative 40 divided by 2 means that, so you know that this a part of, so this is the middle point. So coming towards this side is positive, going towards that side is negative. The same for the Y2. This side is positive, going that side is negative. Z2, up is positive, downwards is negative. So if you do negative 40 divided by 2, that's like how? So it means that the X, which is this length, like it should be equally divided into the negative and positive region. And then we are going to do same for the Y as well. Charlie, I'll start with. I know we'll start from that place. No, lambda divided by 2. No, it was a mistake. I mean, yeah, I said it's supposed to be divided by 2. So, but 0, the Z is going to be 0 because you want the ground to be lying exactly in the region. So after that, you click on apply. Okay, fit to fill. So you will see that the cylinder is lying exactly in the middle. Now, I said that not everybody will be able to like see. So the few people who are very close and are able to see, after that, just help your colleagues. So the next thing we are if you are doing this, I advise you get like a mouse. If you are very conversant with this, the touch pad, fine. But if not, you can get a mouse because me, I'm conversant with the mouse than this. So you have to draw the port that connects the cylinder to the ground. And to do that, you first have to come here, change the drawing plane from SY to YZ. Now, when you do that, you come to orient and then you select front, fit to fill, and then now you come select rectangle. And then you start your drawing exactly from this point, like the very edge of the cylinder. You click and then you drag all the way through. Now the rectangle is supposed to like cover the whole space of the cylinder from this point all the way to this point. But you see that it is not touching exactly the end. That is fine. Sometimes you'll not be able to draw it and it will touch exactly, but then after drawing you go back and change the dimension so that it touches very well. So you just click and you have your rectangle there. You come and you can rename that rectangle as what? pot. Give it any color you want. And then you come to the dimension. Now it is touching both the cylinder and then the rectangle, but it's just left for it to touch the very edge of the cylinder. And that dimension is the Y. So you know that the radius of the cylinder is what? 0. What? Yes, and twice of that is like the whole Y dimension, right? Which is 0.125. So you just come here and then you input your 0.125 there. When you click apply, you will see that it has shifted and is touching exactly that point. You click OK. Now basically you've done majority of the work. What is left for you is to assign various materials and excitations and boundaries, and then draw a radiation box. Now you see all these things are supposed to be assigned, but they are lying beneath the unassigned, which means that you've not assigned them, so you have to assign them. So you click ground, you select ground, and then you right click, and then you go to assign boundary, and then you give it perfect E. You click on that. Okay. Now on the port you have to assign it. To assign the port, you select, you right click, go to assign boundary, assign excitation, and then you come to port, and then you come to lamp port. But if you click this, what you're supposed to get, you will not get it, because I don't know, maybe I've checked that. But if you start your design, then you don't check what I was telling you guys to check for modal and terminal. So you come to HFSS, you look for solution type, and then you see, yes, it is a terminal. So you have to check modal. So I'm coming, let me show you something. So when you come to assign, I think, boundary, excitation, port, lamp port, you see this is what is going to come, which is not what you are supposed to get. You are supposed to get something else, but because you've not checked the modal, you see this one is saying reference conductors for terminal, because you are using terminal. We are not using terminal in this, so you have to come and then check modal. And now come back. Now this is what you're supposed to get. So you click next. You see the 50 that was there. So remember from class 4 told you that the impedance then there is 50. So that's just it. So you come and then you select new line here, and then you start from here. You click and then you draw a line all the way to the top till it touches that very point, and then you click. When it shows defined, it means whatever you've done is right. So next, and then full port impedance is 50, and then you get to school, ensure that it is that, and then you click finish. And to check if your necessary things have been assigned very well, come to excitation. Sorry. So when it changes, you are able to, when you click on the excitation and it changes to this, seeing the line there, it means that whatever you've assigned has been assigned perfectly well. The perfect is for the ground. If you select orient, let me say, and then you click on perfect E, the ground also changes. It means that I'm also going to assign very well. So now the next thing you're supposed to do is to give it a radiation box. So after that you can come back and recheck this to XY, and then now a radiation box. So you just stand anywhere, click, and then you draw your box. Come and name it either rad box or air box. And then you let the material be vacuum because it's a space, and give it any coloring. And you increase the transparency so that you can be able to see see through the box. Now we want everything that we've designed to be lying perfectly well in the box, so we have to choose dimensions. Ensure that your ground is not outside the radiation box, it should be inside, and then your monopole should not be outside the radiation box. So now we know that the height of our monopole is what? What's the height of our monopole? 25, right? So for the Z size is going up. I want everything to lie in the middle. So if the monopole size is 25, I can decide to use twice of that, which is 50. Now for the Y, the ground plane is 40 by 40. So for the radiation box, X and Y sizes, I am not supposed to choose anything less than 40. You can choose from 40 upwards. It's going to have everything inside. So I'm going to choose 40. And for this, I want everything to lie inside. So just like I did for the very first one, half of that, and this half of the Z as well. So when you rotate, you see that everything is lying inside, but I can see that my monopole is like, I think, exactly at the end there. So I'm going to increase the Y size a bit to say 60, and then make this 30. So now you can see that everything is lying perfectly well inside. So you now click on airbus and then assign boundary and then assign radiation to it. Okay, then that is checked. Now we are done with the design. So the next thing you have to do is to do the necessary things that will help you be able to plot your result. So when you come to HFSS here and then you click validation check, it tells you, or it's going to show you the list of things you are supposed to do to ensure that you have designed the antenna and ready to simulate and plot your result. So when you click, you see that everything has been checked except analysis setup, which means that you've not added an analysis setup to be able to run your antenna. So you will come to analysis here, you right click and then you add solution setup, you go to advanced and you input your frequency here. The frequency is 3 GHz. Maximum number of passes, you can make it 10. You can keep that as it is. And then you come here, instead of interpolating, you make it fast. So there are just two ways of representing the same thing, but interpolating means that it's like, okay, let me use this analogy. Two students, you are supposed to draw a curve, right? And then the curve that you are supposed to draw, you have various frequencies that you are supposed to cover. Now the interpolating student is the very smart student. He decides to pick a certain value around the center and then you draw the curve at that point and then interpolate the rest of the values to left and to the right and get the curve in that shape. But for fast, the fast is that type of students that decides to do the curve, draw the curve from the beginning and then assume or guess a certain value, guess values to suit the way the curve is going to be and then he waits to see if the simulation is going to run in the same curve. Until he sees that there is a change, then you wait or you stop the simulation and then change the curve again. I don't know if you get what I'm saying. So that's just what the fast and interpolating means. But for your design purpose, you choose fast. And then when you come here, linear count, you change it to linear step. And then your step size, since your center frequency is 3, that's what you are using. For you, it's going to be different. So you choose a range of frequency, start and stop and the end. You choose a range of frequency that's going to have your center frequency within it. So because you are using 3, I'm going to choose 2.5 and end at 3.5, and my step size, I'm going to choose 0.02. Now the step size, the smaller it is, the more smooth your curve is. So if you choose a very huge value, it means your curve, someone's curve will look very smooth, but yours will look like broken lines. So that's what the step size also does. And you can preview how it is going to look like from here. And then, okay, so when you come back and then you check validation, you see that now everything is checked, which means you can go ahead and then run. So I will validate. Sorry, I will analyze. So analyze. So while it is analyzing, I will go back and add far field. So you come to radiation, you right click, and then you go to insert far field setup, and then you go to infinite sphere. And for this, you change it to 0, and then this to 360. Now this is just a file. Remember from your class, the one of the slide has E plane and the H plane. So this is representing the E plane, and this is representing the H plane. So this one is from negative 180 and then to 180. So this is the E plane. You see that from the result, the one that is like a donut with a red coloring. So it tells you how the energy is distributed around that. So you see that when you start from one point, you go all around and you see that they are all red, which means that is like from 0 to 360 is all red. But then the E plane, it doesn't give you the distribution of the power. It just gives you you see the donut has like bulges from up and then down. It just tells you how tilted your friend is saying the distribution is, the energy distribution is. So that is why this one is running from negative 180 to 180. So it's just like in the vertical, but this is like the whole circular. That's why we choose this. So 0 to 360 and then negative 180 to 180. Okay, so our simulation is done. So when you want to plot your results, you come here, right click, and then you go to modal solution data report. You come to rectangular plot, and then S parameter is selected, which is SY1, and check that it is dB, and then new report. And you see that my frequency, the frequency we used was 3, and this is 2.9. I think it's even more than 2.9, very close to 3. Like we said, you don't have a perfect antenna, so definitely there are going to be a few like reflections. So for that matter, you're not going to get your antenna exactly on your frequency. It should be very close. So to check my frequency, I can just add a marker. And so my frequency, my resonating frequency is 2.91, which is like very good because the center frequency is 3, and then I'm getting my antenna resonating around 2.91 something, which is like very cool. But then if you feel like you want to do optimization to your antenna to drag it a bit closer to your resonating frequency, there are a few things you can do. The first thing is you can change the size of the radiation bus. The size of the radiation bus can change your result. The monopole height, even though you've gotten 25, you can still increase it a little or decrease it a little. Now mind you, if you want to make the increment or decrement, an increase of 0.001 can cause a significant change in your result. So if you want to increase your monopole height, don't move from 25 to say maybe 30, no. You move 25 to 25.01 or 002, something very small, because a little change in the monopole height can alter your result. So that's another thing you can optimize your result with. The next thing is the ground plane. You can change the dimension of the ground plane as well. Mind you, it shouldn't be something you don't move from 40 by 40 to 50 by 50 or 50 by 70, which should be like something very small. And then the grab tool, like I said, you can choose from 0.12 to 0.125. So if you use 0.12 and the result is far away from the resonating frequency, you can just tilt it a bit, like change it a bit from 0.12 to 0.121, 122. And mind you, whatever you are doing, you'll be checking to see how it is affecting your result. So if you increase the height of the monopole and you see that it is sending the result away from the resonating frequency, it means that you should reduce it instead. Sometimes you reduce to a certain point and you see that it is not causing any change to the result. You stop. It means that that is the highest threshold for that particular thing that you are changing. Then you move to another thing. Say maybe you've changed the height and then you've changed it to a certain point and you see that it is not doing anything better to the result again. Leave it that way and go and change something else. So after plotting the first result, you plot your VSWR as well. Be sure to make sure that the function is on none, because VSWR doesn't have any dimension or unit of measure. This is also somewhere close to me. And then the next thing will be your H plane, E plane, and then again. So for A plane, you come to create far field report. And then you come to radiation pattern, you click, and then you select gain together with gain phi together with gain theta. And this is in dB. Now the primary sweep is theta. You come to families, and then for phi you click and then you select 90 degrees. So phi 90 degrees for families, and then trace the primary sweep is theta. You should have something like this. The red one should be as small as possible. It shouldn't be very big. Some designs you finish and you see that it is very big. It should be very small because the red is our wanted radiation. And then that is your E plane. For H plane, you come the same far field report, radiation, and then gain phi together with gain theta dB. But for this one, you are going to change the primary sweep from theta to phi, and then you go to families. The theta, you select 90 degrees. New report. And then this also should be very small. And the last thing, the gain. I think the 3D polar plot. So gain total. Oh, am I doing wrong? Okay, I'm coming. Before then, when you plot this, we are supposed to see your bandwidth and then fractional bandwidth, and upper and then lower frequency. So this is a negative term dB mark that we've been talking about. So when you go to add marker, add Y marker, you see that you can drag this line all the way from here. Yeah, class. So this is your lower frequency, and this is your upper frequency. Now you click and then you add note. When you click and you add note, you can type bandwidth equal to upper frequency minus lower frequency, and then you put the result there. Okay, and then so we are expecting to see things like this. You add notes to explain where your bandwidth is, and then fractional bandwidth. The fractional bandwidth is just your bandwidth divided by the center frequency, and then multiplied by 100, which is going to give you the percentage. So these are the things you are expecting to see. And then you do same for your VSW out. So you add the markers and then calculate for the bandwidth and the fractional bandwidth for that as well. The gain, the one that looks like donuts, I don't know what I'm doing wrong, but when you watch the video, you see exactly what you're supposed to do to be able to plot the gain. So that's just it. Thank you.